Today we're going to talk about second-order linear differential equations. Before we do so, let's review some ideas from before about repeated eigenvalues and zero eigenvalues. Recall that we're considering a two-dimensional system of equations, that is, dy dt equals a times y, where A is a 2 by 2 matrix. We have three concepts that go along with this matrix. First is that of an eigenvalue. This is a root lambda of the characteristic polynomial, determinant of A minus lambda times I2, the 2 by 2 identity matrix. We can express this using the quadratic polynomial. That is, lambda equals negative p plus or minus the square root of p squared minus 4q, all divided by 2. We see that the roots lambda 1 and lambda 2 are non-zero if and only if q does not equal to 0. And the roots are distinct, that is, lambda 1 is different from lambda 2, if and only if the discriminant p squared minus 4q does not equal 0. An eigenvector associated to an eigenvalue lambda is a non-zero vector v such that a times v equals lambda times v. If the eigenvalues lambda are real numbers, then we can choose the eigenvectors to be real as well. However, if the eigenvalues are complex numbers, then we can choose the eigenvectors to be complex conjugates of each other, as the eigenvalues are complex conjugates of each other. And finally, an equilibrium point is a vector y0 such that a times y0 equals the zero vector. We have seen that there are different classifications of these equilibrium points y0 depending on the discriminant of our quadratic polynomial. If our eigenvalues are real numbers, we have three classifications. If both eigenvalues are negative, we call the equilibrium point a sink. If both eigenvalues are positive, we call the equilibrium point a source. If one of the eigenvalues is negative and the other is positive, we say that our equilibrium point is a saddle. We don't yet have an idea of what to call the equilibrium points if one of the eigenvalues is equal to 0. On the other hand, for eigenvalues that are complex numbers, we have the following three classifications. If the real part of our eigenvalue is negative, we call the equilibrium point a spiral sink. If the real part of the eigenvalue is positive, we call the equilibrium point a spiral source. And if the real part is equal to 0, we call the equilibrium point a center. Using all of this, we have the concept of straight line solutions. These are functions of the form e to the lambda t times v plus y0, which are simply on lines that are in the direction of the eigenvector v going through our equilibrium point y sub 0. If there are two distinct real eigenvalues, that is, the discriminant is positive, then the general solution is a linear combination, capital Y of t, equals k sub 1 times y sub 1 plus k sub 2 times y sub 2, where y sub 1 and y sub 2 are two straight line solutions corresponding to the distinct real eigenvalues. If there are distinct complex eigenvalues, that is, the discriminant is negative, then the general solution is a linear combination C1 times y sub re plus C2 times y sub im in terms of the real part of the straight line solution y sub 1 and the imaginary part of the straight line solution y sub 1. Last time we had a couple of motivating questions. If there are distinct eigenvalues, then we see that we have methods of finding the solution in terms of real value functions. But what happens if the discriminant is equal to 0? That is, there are repeated eigenvalues. The origin, y sub 0 equals 0, comma 0, is the only equilibrium point if and only if A is a non-degenerate matrix. This is equivalent to saying that Q is equal to 0, not equal to 0. But what are some equilibrium points if Q does equal to 0? That is, what happens if there are 0 eigenvalues? We have the following proposition that discusses what happens when we have repeated eigenvalues. Let's say that A is a 2 by 2 matrix with only one eigenvalue, lambda. We really have two cases to consider. First, let's say that A is a scalar matrix. Then for any basis, v1, v2, then the general solution is, in terms of straight line solutions, that is e to the lambda t v sub 1 plus y0 and e to the lambda t v sub 2 plus y0, where y0 is just the zero vector. On the other hand, say that A is not a scalar matrix. Then we can find a basis in terms of an eigenvector, v, and a generalized eigenvector, w, satisfying a minus lambda times I2 times v equals 0 vector, and a minus lambda I2 times w equals v. Then the general solution can be expressed in terms of two functions, y sub 1, which is e to the lambda times v1, a straight line solution, and a new one we haven't seen yet, y sub 2 equals e to the lambda t times v plus w. We have a similar concept of behavior when we have a zero eigenvalue. Let's say that this eigenvalue is lambda 1 equals 0, and that lambda 2 does not equal to 0. Then in this case, our matrix A has distinct eigenvalues, so we can find a basis in terms of y sub 0 and v2, where a times y sub 0 equals the 0 vector, and a times v2 equals lambda 2 times v2. Then we can express the general solution as a linear combination of y sub 1 equals y sub 0, that is an equilibrium solution, and y sub 2 equals e to the lambda 2t times v2 plus y sub 0. That is a straight line solution. Today, we're going to use all of this to discuss how to solve second order linear equations. First, let's consider a two-dimensional linear system with constant coefficients. That is, dy dt equals a times y, where A is a 2 by 2 matrix. We have seen that if x and y are solutions to the system, then they are both solutions to a second order equation, d squared y dt squared plus p times dy dt plus q times y equals 0, where we can express p and q in terms of the coefficients of our matrix A. Conversely, given a second order linear equation, we can express this as a two-dimensional system. That is, d squared y dt squared plus p times dy dt plus q times y will correspond to a capital Y as lowercase y comma v, and our matrix capital A being 0, 1, negative q, negative p. Now that we know how to solve a two-dimensional system, can we use this to solve a second order equation? Well, first, let's recall an algorithm of how to solve said two-dimensional linear system. The idea is that we like to write our solution, capital Y, as a linear combination of k sub 1 times capital Y sub 1 plus k sub 2 times capital Y sub 2. Our algorithm is in 3 steps. First, we compute eigenvalues as roots of the characteristic polynomial. Second, we compute eigenvectors v1, v2, and a generalized eigenvector w1 if necessary. Recall that the eigenvectors v satisfy a minus lambda I2 times v equals 0, and the generalized eigenvector satisfies a minus lambda I2 times w equals v. Third, we'll then compute real valued functions y sub 1 and y sub 2 as listed in the table below. Here, notice that we've broken it into 3 cases depending on whether the discriminant is positive, 0, or negative. If the discriminant is positive, we simply take the straight line solutions. If the discriminant is negative, we take the real and imaginary parts of the straight line solutions. But if the discriminant is equal to 0, we have to be a little bit careful that we may need to involve a generalized eigenvector. Using all of this, we are now motivated by the following algorithm to find a general solution to our second order equation. That is, we want to write our solution in the form y sub t equals k sub 1 times y sub 1 plus k sub 2 times y sub 2. Now, we only have 2 steps in our algorithm. First, we'll compute roots lambda of the characteristic polynomial, lambda squared plus p lambda plus q. And second, we'll compute real valued functions y sub 1 and y sub 2 as in the table below. Here, again, we've broken our cases into 3, depending on whether the discriminant is positive, 0, or negative. If the discriminant is positive, then just like with the straight line solutions, our solutions will be e to the lambda 1t and e to the lambda 2t. However, if the discriminant is negative, then here we need to take a look at the real and imaginary parts. Recall that Euler's formula states that we would have e to the alpha t cosine beta t and e to the alpha t sine beta t. Finally, if the discriminant is equal to 0, we have to be a little bit careful because we only have one eigenvalue. In this case, we can write our solutions as e to the lambda 1t and t times e to the lambda 1t. As a remark, you'll notice that this is much simpler than solving a two-dimensional linear system with constant coefficients because we do not need to compute eigenvectors. In fact, it's actually very easy to find eigenvectors associated to our matrix A. In particular, if lambda is a root of the characteristic polynomial, then it is an eigenvalue, and hence the eigenvector v can be chosen to be 1, lambda. Let's end today by going over some examples on how to solve these second-order differential equations. First, let's try to find the solution to the initial value problem, d squared y dt squared plus 7 times dy dt plus 10 times y equals 0, where initially y of 0 is equal to 2, and the derivative dy dt evaluated at 0 equals negative 13. First, we'll find the roots of the characteristic polynomial, and we find that these roots are lambda 1 equals negative 5 and lambda 2 equals negative 2. Second, we can list the general solution according to the table below. In this case, our roots are real numbers, so we simply have case of 1 times e to the negative 5t plus case of 2 times e to the negative 2t. We'll compute the derivative y prime because we'll need this in just a moment. Finally, we can find the constants k1 and k2 based on the initial conditions. If we plug in t is equal to 0, we find that k1 plus k2 equals 2, and the derivative y prime at 0, which is negative 13, equals negative 5k1 minus 2k2. Therefore, we find that k1 is equal to 3, and k2 is equal to minus 1. This means that the solution to our initial value problem is 3 e to the negative 5t minus e to the negative 2t. Let's do something similar here in our second example. Now we'd like to solve the initial value problem, d squared y dt squared minus 8 dy dt plus 16y equals 0, where now y of 0 is equal to 3, and the derivative dy dt evaluated at 0 equals 11. First, we'll find the roots of the characteristic polynomial. In this case, there's only one root, namely lambda is equal to 4. Second, we'll find the general solution using the table below. We find that this is k1 e to the 4t plus k2 times t e to the 4t. We compute the derivative because we'll need it in just a moment. Third, we can find the constants k1 and k2 based on the initial conditions. Initially, at t is equal to 0, y of 0 is equal to 3, which is k1, and y prime of 0 equals 11, which is 4k1 plus k2. This means that k1 is equal to 3, and k2 is equal to minus 1. Hence, the solution to our initial value problem is y of t equals e to the 4t times 3 minus t. And finally, let's consider one last example. Let's solve the initial value problem d squared y dt squared plus 4 times dy dt plus 13 times y equals 0, where y of 0 is equal to 1 and dy dt at 0 equals negative 2. First, we can find the roots of the characteristic polynomial. We find that they are complex numbers. Lambda is equal to negative 2 plus or minus 3i. Second, we'll find the general solution based on the table below. Remember from Euler's formula that we would find k1 times e to the negative 2t cosine 3t plus k2 e to the negative 2t sine 3t. As before, we'll take the derivative because we'll need these expressions. Finally, we can solve for k1 and k2 based on the initial conditions. When t is equal to 0, y of 0 is equal to 1, which is case of 1, and y prime of 0 equals negative 2, which is negative 2k1 plus 3k2. We find that case of 1 equals 1 and case of 2 equals 0. Hence, the solution to our initial value problem is e to the negative 2t cosine 3t. Thanks for watching.